So the stage is yours.
Thanks, Andre. Good to be here. I'm glad to see so many folks have hung on for the final talk. Can everybody hear me okay?
Yes, I can hear you.
Okay. It looks like the share button has not come active on my end yet, Andre.
Yes, we had this issue multiple times. Maybe someone else can talk into the microphone. Then I can make Eric the presenter. Ja, dann taucht er erst auf der rechten Seite in der Mitte.
1, 2, Test. 1, 2, Test. Pink Floyd.
Still no luck.
John Pickering still has the presenter token.
Sorry, no, it looks as if I could still share, so perhaps you've got to disable me as presenter.
Ah, I see it now. Okay, there we go.
Okay, perfect. Thanks.
Yeah. Okay. Can everybody see my screen?
Yep, but not you.
Ah. Well, believe me, John, I'm not the main event here. Let me see if I can activate my camera real quick. There we go. Okay. I guess we're all set. I'll go ahead and get started. So hello from sunny California, everyone. Like I said, I'm really delighted to see, that everybody's hung on for the last presentation. Thanks very much for having me. My name is Eric Modica. I'm a design manager in the Precision Converter Group at Analog Devices. And I've been with ADI for about 19 years. And in the winter of 2016, I had just taken over a project to second source the LTZ-1000, which you all know, and this was obviously before the merger with Linear Technology. The primary reason ADI started to look at second sourcing the LTZ was because one of our VPs saw an ADI app note that used the LTZ-1000 as the reference for a 20-bit DAC, and that was the AD5791. So by the time I took over the project, there had been a couple of test chips to try look for various candidates for internal processes to use at ADI to match such a part. And the best thing I can say is that we learned very slowly what not to do. And so I thought to start the talk off, it would be entertaining to look back on some of our development foibles on the way to success. I think the Germans have a word for this, Schadenfreude, pleasure in other people's misfortunes. So that's what I'll start the talk off with. Okay, so probably the most important specification, as you're all aware, for these types of parts is the stability for use in transfer standards. So the first thing we evaluated and how we determined that success and failure was long-term stability. Our first attempts were on SOI processes, and I can only imagine that this was a convenient way of isolating the Zener so that we could eliminate the inconvenience of running the substrate above ground. And this was our first result out from a 36 volt dielectrically isolated bipolar process. And as you can see, the early life is horrendous, and even after the first 1,000 hours, there's hundreds of ppms of long-term drift, out to 5,000. And this was with yet another DI process that had 5 volt CMOS integration. And at this point, we kind of raised the white flag and gave up on larger scale integrations and went back to our bipolar roots. And so we selected a process that was very similar to LT standard bipolar. We learned that in retrospect, circa 1985. And this was to do our best to mimic the doping profiles of the LTZ. And this was the final result of that. And it's important to note that these measurements were all initially taken with unheated buried Zeners in oil. This is how our long-term drift setup is. This is how we have our long-term drift set up. So we have a back plane with a bunch of line cards, and we can put these individual DUTs in there and get large quantities of these things, so we get decent sample sizes. You can see in a lot of these plots that there's some wavering, really long time constant wavering going on. And we found out later on, it's kind of interesting that oil is actually hydrophilic. So humidity can pass through the oil into the PCB. It's not actually affecting the part directly because these are all hermetically sealed, but the PCB is hydrophilic, so it's absorbing humidity, and that stress gets referred back to the die. So when we look at a part like this, you can see this ripple. That's just due to humidity, and we know that because we track that. Okay, and so once we selected the right process, another issue we faced was gross tempco errors, even with ovenization active. So this is a plot of the LTZ 1000 and the ADR 1000 normalized to a single voltage at around room temperature. And as you can see, the ADR 1000 tempco is about 100 times worse than what you get with the LTZ. And this is where things got, pretty comical, because between Paul Hanus and I, who was helping me out on this design, we each had about 40 years of bipolar, or we had a total of 40 years of bipolar design experience between us. Paul's retired and well into his 80s now, so he had about 35 of those, and I had about 5. And together we came up with all sorts of crazy theories as to why this was happening. Maybe there were hot spots in the Zener. Maybe the fact that we didn't have fancy glass balls in the die attach created pockets or planarity issues, which introduced gradients. And we burned about a month of time with theories that they would make flat earthers blush. And mind you, we were struggling with this sometime after Analog had announced it was in negotiations to purchase LTC. So in our minds, the project was likely going to get shut down, but we were invested enough emotionally that we didn't want to admit to Dobby, that's Bob Dobkin, when we eventually met him, that even after 4 years of R&D, ADI couldn't second source a 30-year-old part. So at some point, the engineer in both of us took back over, and we started going back to basics, and that took us to focus on the concentric heater rings on the part itself. So here I'm drawing a cross-section of these rings, and I draw a cut line through the outside, and you can see the heater ring looks like an NPN transistor, and this is true of the LTZ 1000 as well. The primary resistor is made up of N emitter, which sits in P base in an epi tub, and you have P substrate on the outside as the substrate. And the top side of the heater, which is pin 1, we have all of these diffusions tied together. Okay. So as a schematic representation, when you draw this out, the heater and the associated parasitics look something like this. So here's pin 1 and pin 2 down here. This is the actual resistor that conducts the current. P base and NBL resistors are just there for illustrative purposes. But so you have this NPN here. That's the cross section of the heater. But there's also a PNP to substrate, a parasitic PNP with the emitter equal to P base, the base equal to epi, and the collector equal to substrate. Now keep in mind that injection to substrate is not always a problem in ICs, but on this part, it's a huge problem because the substrate is right here in the schematic representation, and it sits a VBE above ground. So any disturbance on this node would mingle directly with the reference currents in an open loop fashion. But assuming we have our trusty level shifting diode in the circuit, and we most certainly did, we just couldn't wrap our minds around how we were getting injection into the substrate. So upon closer inspection of the heater contacts, we found that the original designer had properly contacted both the N emitter and the P base by inserting a slit in the N emitter ring. So this is the effective pin 1 contact on the heater right here. And so this slit in the N emitter ring allows us to make contact to the P base so that they're effectively shorted together. And in those days, P base by itself was heavily doped enough where you didn't form a Schottky barrier diode when you contacted it. However, mysteriously, there was no such slit on pin 2, which is the lowest potential in the heater. And consequently, when we swept temperature cold and demanded more current through the heater, the NPN emitter dropped in potential with respect to the base. And once that device saturates, that is, the collector drops below the base, the parasitic PNP starts broadcasting holes to the substrate, which is directly to the core of the reference. So going back to the schematic, what was happening is as we swept cold, you're conducting current in this N emitter, so there's a drop from here to here. P base was pulled up high over here, but floating down here. So that allowed N emitter to drop with respect to P base, which turned this device on. As this device turns on, you pull current through the N buried layer, and that eventually saturates this device, powers this PNP up, and injects substrate current directly to pin 4. And it doesn't take much current at all to cause the gross Temco errors that you're seeing there. And that's something like you would get if you forgot to put the level shifting diode at the bottom of the heater. But we were seeing, tens of microamps out of tens of milliamps of current, and you get those kind of results. So that gives us a good excuse to look at the cross-section of the core for a moment. And this, again, is valid for both the ADR100 and the LTZ1000. So I've drawn a dotted line right through the center of the die. Here's your concentric Zehners, your concentric Zener ring, and then the Q2 temperature sensor out at the edge here. Note that what makes this a buried Zener is the overlap of the isolation diffusion here and the P base only at the bottom of the diffusion. So that means that the periphery has a higher breakdown by about 600 to 700 millivolts than does the bottom plate of the Zener. So this would break down as at 7.2 volts for the 7 volts for the LTZ1000, or maybe it's you guys know better than I do, 6 point something. And for the ADR1000, it's more like 6. So, and then the other tricky thing about this is that since the ISO is diffused all the way down to the substrate, as I said, that the anode of the Zener contacts the isolation. And so you're forced to raise any unrelated epipockets, for example, the heater or diode above substrate, to keep that Zener from being disturbed. So when I first had the opportunity to talk to Carl Nelson about why he chose not to pull N buried layer underneath this isolation to, in effect, isolate the Zener, his best guess, because this was so many years ago, was that they were concerned about crystal defects that might be introduced in the vicinity of the buried Zener. And that really is the biggest hurdle to designing a fully integrated part. Putting more onto this would just be really tricky with having to raise all the NPN collectors a diode above this guy. Okay, so this is a side-by-side comparison of the two parts. Here on the left, you have the ADR1000, and on the right, you have the LTZ1000. So as you can see, we borrowed quite a bit from the original design. If I were to do the part all over again, knowing what I know now, I would have likely, isolated the buried Zener and used transistor-based heaters so that users never run into headroom issues on the heater driver, and also so that we don't waste power in the heater driver. That's another drawback of the LTZ architecture, is that you burn, quite a bit of power in the output driver, and that's really wasted. The part could use that to bring itself to temperature. Also, just the stickler in me notes that the Zener, the temperature sensor, and the compensating VBE are not on the same thermal center line. That is, for a given ambient temperature, the parabolic gradient has Q2 slightly hotter than the Zener ring, slightly hotter than Q1. Okay, and the other thing that's interesting to note, and I see discussions on this just even recently on EEVlog, is the original LTZ 1000 had these multiple concentric heater rings. And I know there's a lot of discussions and theories about why these are there. And first, I believe that Jim Williams used a similar arrangement to make the LT1088 RMS to DC converter. But also, when you start to look at the stability of any thermal feedback system, the transit delay from the heater to the sensor plays a big role in determining the effective loop phase margin of that loop. So in theory, a trade-off exists between the thermal gradient and the thermal stability. That is, the closer the rings are to the core, the less phase delay is introduced in the feedback. But that would cause a larger gradient between Q2, the Zener, and Q1. So the fact that this was a kit part makes me think that, both Jim and Carl were using this for their own purposes. Jim was using it to create an RMS to DC converter, so he just wanted the thing to run fast. So he wasn't using the Zener. He was using the temp sensor and the heater. However, Carl had to be very concerned with this phase delay effect and also gradients. If you move the heater infinitely far from the sensor, what you get is basically a bang-bang controller. The heater heats up, it takes too long for the sensor to pick it up, and so consequently that control loop just bangs back and forth in between the rails. Okay, another important aspect that carries over to the ADR1000 is the benefits of the bake and burn process. So when I first started working with buried Zeners and VREFs in general, the conventional wisdom was that bake and burn sped up the aging of the part, and that one could, accelerate the early life drift to finish up sooner. That's this area here. That's the majority of your drift on parts like this, your uncertainty. So I've learned enough in my years working in analog design not to make broad generalizations, but what I've observed is that bake and burn is helpful primarily for low frequency noise reduction in this context. We've had tier one manufacturers tell us the same thing when we sent them ADR1000s prior to instituting a bake and burn. Most of the parts look okay from a low frequency noise perspective, but if you look at enough, you'll find one that's extremely noisy and actually remedies with a bake and burn. So only being a process hobbyist myself, the only explanation I can give there is that you have these dangling hydrogen bonds at the surface of the SI, and sometimes that amounts to surface charge. And if that ends up in the vicinity of the Zener, if you're unlucky enough, then this is the kind of thing that you get, and it's really the only thing that would move at such low temperatures that where you're running a bake and burn, say at like 150 C. Okay, so I also want to discuss some of the documentation that we've added into the ADR 1000 datasheet, because I do think it's quite a bit more complete than what was included in the LT datasheet. And I think it might help ease the burden of designing the part in. First of all, we've included a lookup table for the temperature set divider to help you tune the right chip temperature for your application. So the name of the game is you really want to minimize T-rise for a given ambient temperature, and through that you realize a improved tempco because you're effectively reducing the on-chip gradients. So it's good practice to set your chip temp as low as your application plus margin will allow. Also, we always get asked about how sensitive the reference is to a given resistor in the application circuit. And there hasn't always been a concise answer until now. So table 7 shows attenuation factors for every resistor in the typical connection diagram. And we've been able to come up with this by using our models to simulate the thermal feedback portion of the ADR 1000. So for example, this plot shows ppm drift normalized at room with the Zener set resistor R1 with 0 tempco in orange, and then reprogrammed with the 10 ppm per C tempco in green. And as predicted by the table, the 10 ppm sees an attenuation factor of 340, giving the part, the performance of the part a total drift of 0.03 ppm per C. Okay, so it's interesting to note that to do this estimate for the resistors in the heater loop, we have to make some assumption about the raw unheated tempco for a given Zener bias, because R3, R4, and R5 form the temperature set divider in the thermostat, are impacting the set temperature of the part. So you have to make some assumptions. If this divider moves, how much is and thus the set temperature of the chip moves, how much is my part, how much is the raw reference going to change with that? And that's really dependent on, the current that you're burning in the Zener and also the current that you're burning in the temperature compensating diode, Q1. Okay, lastly, we also get a lot of questions about what op amps to use in the application circuit. And it's generally with an eye towards reducing long-term drift or tempco or noise. However, the fact is most precision op amps won't have a huge impact on these parameters because of the gain provided by Q1 and R2. So this is essentially a common emitter gain stage, and you've got about a gain of 230 here directly into a unity gain compensated amplifier. So this guy, it's easy to get plenty of op amps that have gains in excess of 1 million. So things like noise, offset drift are attenuated by this 230 gain factor in this common emitter stage back to the reference. The one exception to that is the base current in this amplifier. So you really don't want a large variation in base current in the region of operation in the common mode of this amplifier, which is a diode off ground. You want this IB to be relatively constant because it does look like a leakage, as I described in the heater example, and it mingles open loop with the currents, with the current in the zener. Okay, so this is a bit of a marketing slide, but I thought it would be useful for a lot of the folks to see kind of on a scale the ovenized parts that we offer today at ADI. And it also tells you a little bit about how we're looking at noise these days. So what we like to do, and I think Keysight does something similar to this, is we look at each sample for 15 minutes. And each observation on this histogram represents a 10-second snapshot, and the peak-to-peak noise in each 10-second snapshot sampled at 100 hertz. Okay, so here you see the number of samples that are rolled into each of these distributions, and then you see the mean and standard deviation of that noise reported back. That's in the peak-to-peak noise. So on the far left, you have the LM399, which is still a very good part compared to references in general. And then this might be new to a lot of you, the ADR100X, which we'll be releasing this year. This is a next generation of the 399, which we kind of viewed this as low-hanging fruit. People had been asking us for a while. We just burned 4x the current in the zener on this guy to get a 2x noise reduction. And we also were able to get the dynamic impedance down quite a bit through some minor design modifications there. So this will be releasing this year. And then there's the LTZ1000A and the ADR1000 at the quietest. Okay, so that leads us to the what's next portion of the presentation, and what's with the ADR100X in the title of this talk. And the X is there because we look at this as a family of parts, and from the learnings we had on the ADR1000, our primary objective since releasing that part has been taking those and trying to develop a easier to use part, but still with some flexibility built in so that the experts like you guys still find it useful. So the ADR1000, here's the application circuit here, and the components that are included in that and the LTZ1000 are highlighted in blue. And this is what is included in the ADR1001, and you can think of it as this is just a full integration of everything you see here and a few other things. So you'll recognize the IC ovenization on the left here. We've added in some things to make this easier to design in. So for example, you can put complementary supplies across the heater transistor to reduce your current draw. ATE customers often have plus minus 15 volts available on their board. You can modify the chip operating temperature by simply pin strapping the temp set pin to 6.6 volt to the 6.6 volt output to lower the temperature to all the way down to 45 C, or you can pin strap to ground to raise the chip temperature to 120 C, or any value in between, depending on what resistor you pin strap through. If you leave the pin float, the part defaults to a 70 degrees C set temperature, and we'll likely be able to specify the max and min of that in the data sheet. And because we're trimming that now, it will be substantially reduced compared to the ADR and LTZ 1000. The variation due to the temperature variation due to VBE variation of this guy and the variation of the Zener voltage itself. We've also added a power good pin here, which is simply an open collector heater health indicator. So if the heater is in limit or starved of current because the ambient temperature has exceeded the chip temp, power good will pull low and let you know that you're out of regulation. You'll still have access to the 6.6 volt raw Zener output, which we verified has equivalent noise performance to the ADR1000. If you want to buffer that out to a 5 volt converter compatible voltage, you can hook up the output buffer to VD out, and you'll have the world's first, absolute accurate ovenized voltage reference. If you'd like to gain that up, if you'd like 10 volts for talking to a DAC or to your own home rolled converter, you can use this trim divider here, R3 and R4, to put this amplifier in a gain of 2 to get 10 volts out. Okay, so this plot, this is just a preview of kind of the performance we're getting at the 5 volt output on the ADR1001. This compares, here's the 5 volt output with some noise filtering capacitance prior to the buffer. And this is compared to the lowest noise band gap in the world, the LTC 6655 LN with 100 microfarad noise filter cap. And then in green, we have the LTZ 1000 divided down by a factor of 1.4 to normalize it to 5 volts. So even if you assume a noiseless attenuation factor and a noiseless amplifier for the LTZ 1000, the ADR 1001 5 volt output is still lower noise than the LT, and it's actually 3x lower noise than the 6655 at 0.1 hertz. And this is with a 4 milliamp burn in the Zener. And by the way, you still have the flexibility to change the current in the Zener on the 1001. We left that resistor external. Okay, so this is a plot of total reference error versus temperature normalized to 30C of, I think this is 25 units of the ADR 1001. So the total uncertainty of the population is around 10 ppm for 100 degrees C temp span. So, the nominal of this is about 0.05 ppm per C typical TempCo. And if you look at the heater current draw for all of those parts, you see a typical thermal isolation of around 150 degrees C per watt. The nice thing I like about this heater design compared to the LTZ 1000 and ADR 1000 is that it uses just a transistor-based heater. So you don't have the headroom issues. You don't have to be concerned about the headroom issues, the voltage drop across the resistor, crushing the heater driver. And also, you're not wasting the power in the heater driver. All of that goes directly to powering the heater to get the chip, to make the chip as power efficient as possible for a given ambient temperature. The other thing we've built into the heater is there's a built-in short circuit current limit of 100 milliamps. If you want to use external degeneration, you can lower that to 60 milliamps, for example. We've gotten complaints from customers, when you first power the part up, it can load down your pre-regulator if you're not careful. So we've also provided some hooks to make that a little bit easier to design in. Okay, so lastly, these are close to finished versions of both our ADR 1000 and 1001 customer evaluation boards. You can already order this one and we're providing limited samples for the 1001 board to customers late this year. So note that even with some LTC power regulators designed, we've even put the power signal chain in here, we still realize a 3.5x size reduction versus the ADR100 eval board. And it's not so easy to tell from the picture, but there is an acrylic glass shield over this whole thing and around the cutout. So even though the packaging of this part has substantially reduced the thermocouple errors that you see, you still do need to shield this part from air gradients to keep thermocouple noise from ruining the low frequency performance. Okay. And yeah, that's all I have. I sincerely hope you guys enjoyed the talk. I think there's a lot of great experts here, and there's a lot of really good stories. So yeah, thanks a lot for listening.
Thank you, Eric. I think we can give it a clap here.
Thank you.
We have some questions in the chat box. One of them is, did you also try to mimic the flute chip design?
The Flu 1, right?
Yes.
Yeah. We actually, so the Flu 1 layout of the Zener looks a little bit more like a hot dog. So that end emitter diffusion that's a ring in the LTZ 1000 is a long stretched emitter with rounded edges. And it's very big. So I think the bigger you make the Zener, the 1/F noise kind of declines as square root of the area. So we do actually use that design, a similar design on the 1399. But for the ADR 1000, I just wanted to use as we, at that point we were just trying to second source the LT part. So we wanted to change as little as possible. And as you can see, we went through quite a few headaches to try and get to that performance. So if I had to go back and do it all over again, I think the layout for the Flu would work just fine.
Then we have another question. Are there any plans to make an ADR 1000 with improved thermal insulation, such as air bubbles in the die attach or glass bubbles, I think you said earlier?
Right. We're looking into it, is all I can say. Yeah. It's not easy to source. There's a limited supply on the LTZ 1000 side. That manufacturer of those glass beads doesn't exist anymore. So sourcing those things and verifying it, as you can imagine, is quite a task. But we are looking into it.
So just another question. Can you say something about the glass transition temperature of the current die attach?
I don't know the answer to that.
Okay. Then we have a question. How was the dynamic range? The dynamic impedance of the ADR3099 reduced exactly?
How does it reduce?
How was it reduced?
Oh, how was it reduced? By upping the open loop gain in the reference itself. So the dynamic impedance is effectively the output impedance of the output transistor divided by the open loop gain of the amplifier that drives it. So we just basically raise the gain in that amplifier. There's a little bit of a stability trade-off, but we described that very well in the data sheet.
Okay, then we have a question here. Is a burn-in possible with the integrated heater?
That's a very good question. I don't know. It is one of the reasons why we built in the capability to raise the heater, the chip temperature all the way up to 120C. It's not quite as it's not quite as hot as we would run our typical burn-in, but we'll certainly try it, and if it works, we will publish something in the data sheet, because yes, we did think about that.
Cool. So then there's a question, is the ADR1001 monolithic or a hybrid design?
It's monolithic.
Okay. So there was some speculation if you simply combined the LT5400 series resistor with the ADR actually. Is there any SPICE model available for the ADR?
For the ADR1000, yeah, we actually have a much improved model that is waiting to be uploaded to LT SPICE. So yes, there is one, and it actually does include the thermal regulation. So yeah, we're working on it.
Then we have a question. Just feel free to answer or not. Is there any roadmap when ADR 1000 and 1001 could be available to buy normally?
Well, the 1001 is scheduled to release next year, and that is and has always intended to be a broad market part. So that part will be available. The 1000, the ADR 1000, I understand there's some difficulty because this is not an open market release of getting a hold of that part. All I can say is that it's not something that's up to me, and we struggle with the having the people available just to support a broad market release for something like that.
There's a question from John. With a transistor heater, is it a single transistor or say 3 transistors arranged symmetrically?
Yeah, it's a good question. It's not a single transistor, is all I can say.
Then we have a question from Frank. What about operating the ADR at 0 to C for the ref amp?
Oh, sorry, say that again, Andre?
What about operating the ADR 1000 at 0 to C for the ref amp?
For the you mean not running the heater, but operating the raw Tempco at 0?
Yes, exactly. That's what Frank is referring to.
Yeah. Well, you can get there. I think with the raw Tempco on the ADR 1000, the VBE is slightly dominant. That's at 4 milliamps, what we have in the data sheet. So you get a minus 20 ppm per C Tempco. So if you raise the current in the Zener, you can reduce that Tempco even further. I don't recall what you need to. I think it's maybe 8 milliamps. If you burn that in the Zener, you can get the Tempco down to close to 0. Single digit ppms.
Okay, then we have a question. If LTZ1000 is staying in production, what specific application is targeted by each part?
Between the LTZ 1000 and the ADR 1000?
I think so, yes.
I think they target the same applications. Like, as I said in the talk, when we first started developing the ADR 1000, the companies weren't merged. It's a project that never would have taken place if it came to our desks post merger. And in fact, like I said, we fully expected the project to be canceled because, you know, customers are very happy with the LTZ 1000. But it was actually because of people like you guys, I mean, John in particular, that, you know, really saw the value in this part, and CERN as well, Nikolai. And so, you know, they really pushed us to release this part, and that customer feedback is what made that possible. So it's incremental and it's targeted at the same applications, I'd say, but I'm still happy that it was made available.
Yeah. So there's another interesting question. How did you manage to decrease the noise by about 50% compared to the LTZ?
We got lucky. You know, we didn't create any special diffusions. We don't have the resources to put somebody in process, you know, working on this, doing TCAD simulations, especially, you know, not looking at low frequency noise. So what I chalk it up to is that the doping profiles in the ADR100 process are slightly heavier than are the LTZ 1000. Consequently, you get a lower breakdown. So it's more of a Zener than an avalanche diode, and avalanche noise looks like shot noise, and so you can look at it as a coefficient. You know, these Zener diodes all have a avalanche noise coefficient. And since the ADR 1000 trends towards the Zener side and less towards the avalanche diode side, it has a lower avalanche noise coefficient.
Okay, cool. So there are a few more comments. Yeah, a general question, will the slide deck be available after the meeting? So yeah, I leave it up to the lecturers if they want to provide their slides or not. And if so, I would forward them to everyone registered to this event. Yeah, cool. I think for the moment, is there any question from the audience? Yes. So the question was, at which temperature did you make the burn-in?
I believe it's 150 C.
So simply powering the Zener and have the ambient at 150 degrees, and then, what was it, 168 hours or something like that?
Yeah, you know, and we haven't tested the bounds of that. You know, that we basically just copied the bake and burn process of the LTZ 1000, which is 168 hours, both bake and burn. We have at least small sample size evidence that you may be able to get away with just doing an unpowered bake, and that's good enough to dissipate the charge. But I have to say I haven't looked at it really closely.
Okay. So someone asked I should not skip Tin's burn-in question. Did we figure that? What is the special decision to make voltage lower than LTZ1?
Yeah, that was just, there was no, we didn't set out to do that. We used a similar arrangement to get the buried Zener action, as I showed in one of the slides, which is, you know, really just down to overlapping the down ISO diffusion with the P base at the bottom of the N emitter, and that just gives you what it gives you, and so it came out to 6.6 when you include the VBE, and you know, really what got this part released was the fact that it just happened to be so much lower noise than the LTZ 1000.
Okay. Before I ask the cryogenic question, simply have elevated temperature or cycling during burn-in? Because some rumor says cycling around glass transition temperature might improve the aging. Can you comment on that?
Our burn-in process, it doesn't utilize any cycling.
Okay, so we have a question. Yeah, did you try cryogenics temperature operation? How that affects voltage noise? Okay, this becomes nuts.
That's interesting. Yeah, quantum computing is really a big thing, and I know that there's a group inside ADI that looks at that, and I do wonder how much of the electronics, actually have to run at those temperatures, and if they do, well, then it certainly, adds a lot of relevance to built-in ovenization. It kind of infuses some more energy into it, but I think that if you're running the part down at 0 Kelvin, without heating it up, it's not going to work.
Okay.
The electrons will cease to move.
Okay. To whom do we have to speak to order some samples, actually?
Yeah, so my colleagues are actually on the call, Carlos Sanchez and Ray Zhao, and so
Hi, Reza.
so you can contact them.
And I did answer TIN. I'm mispronouncing it. I apologize. We do not sample for free this device. It's expensive. We do sell in limited quantities the ADR100 via ADI's distribution channels. I put in the chat the part number that you can request. It's the ADR1000 AHZ. And there's a minimum order quantity for purchase. We do not support this, as Eric said. It is very helpful that you have experience with the LTZ 1000. That will enable you with your background and of experience to use the ADR 1000, and in the future, the more simplified ADR 1001.
Okay, thanks on that. So one last question, I think. Anyone else? Seems like everyone is fine. Okay, then I say thank you very much. Oh, we have a last question. What technology does the resistor in the ADR1001 use?
It uses a form of thin film.
Okay, cool.
Yep.
So thanks again, Eric, and also thanks to your colleagues. And yeah, big applause. Thank you.
Yeah, thanks for the invite. Pleasure, Andre. Thank you.
Okay, I will leave